The topic of the presentation is efficient multithreading computation of modular exponentiation with pre-computation of residues for fixed base. The authors Ihor Prots'Ko, Aleksandr Gryshchuk, Volodymyr, Riznyk. The affiliation of the authors: Lviv Polytechnical National University and Limited Company SoftServe. The efficient computation of modular exponentiation for big numbers is relevant for solving problem of modern asymmetric cryptography, for the efficient implementation of theoretical and numerical transform, and other applied problems. Many efficient methods of modular exponentiation have been developed and are often used to reduce the execution time of modular exponentiation operation. There are three types of exponentiation algorithm, which include basic techniques for exponentiation, fixed exponent, and fixed base exponentiation algorithm. The modern software libraries are used to implement the computation of modular exponentiation. The software implementation of modular exponentiation is included in the Crypto++, OpenSL, PariGP, peer libraries. The software implementation uses efficient methods for modular exponentiation, which have been developed. Among them are called right-to-left exponentiation, left-to-right exponentiation, sliding window exponentiation, Montgomery ladder, simultaneous multiple exponentiation, and their modification. The algorithm right-to-left binary exponentiation is wide to use. This algorithm, called right-to-left because it scans the exponent bitwise from right to left. The further development right-to-left binary exponentiation is showed the scheme of computation, the modular exponentiation consistently determine residuals. The number raised to the power 2i under modulo. Then these residuals are multiplied. But this scheme has the disadvantages of parallelization. Parallel computation of residuals have different time, and parallel multiplication received residuals needs the synchronization. Our theoretical research denotes that the process of computing residuals is periodic with period and offset. Therefore, for a fixed base of a number of the modular exponentiation, we can speed up the process of computing modular exponentiation by pre-computation residuals of the number raised to the power of 2i under modulo n. The multithreading software implementation in language C++ with pre-computation of residues for fixed base include two parts, pre-compute and parallel parts. The precompute function finds sequence of residuals for fixed numbers, base, and mode, and analysis of periodicity. The precomputation use function find reminders to optimize multiple residuals and function update reminders shortens the length of the sequence of residuals to the end of the first periodicity. To organize efficient multithreading computation or modular exponentiation according to precompute parallel function, I used the thread function. Accordingly, these threads are created to perform the computation of modular exponentiation. The result of the function precompute parallel is written to variable, and the computation time and fixed and averaged to output. To compare the computation efficiency of developed modular exponentiation function precompute parallel for a fixed based with precomputation with three functions implemented from crypto, OpenSL, and peer libraries are used. This table shows the average execution time microsecond of the function of computing the modular exponentiation, where base exponent mod is a pseudo-random data for 1 key bits and 2 key bits, and testing was performed on computer system in processor Intel Core i5 and Intel Core i9. In a result, the developed function precompute parallel speed up the execution of computation of modular exponentiation of big number with 2k bits in comparison with the other libraries. The scientific novelty of obtaining results lies in the implementation of parallelization using multithreading in the algorithm of computing the modular exponentiation, based on the use of the representation of exponent in the form of a binary number and precomputation for a fixed base of reduced set of residuals. The practical significance of the works lie in the fact that obtained results can be successfully applied in modern asymmetric cryptography for efficient computation of number theoretic transforms and other computational problems. The especially effective will be used function precompute parallel for application with fixed base exponentiation in elliptic curve cryptography, for instance, for Diffie-Hellman agreement and elliptic curve digital signature algorithm verification. Prospects for further research are the development and implementation Montgomery modular multipliers in the developed function precompute parallel of multithreading computation, the modular exponentiation for big numbers. Thank you for